Hello everyone, I hope you are fine. Today we are going to continue the chapter about uh, analyzing beams and drawing beam shear force and bending moment diagram. As you remember from the previous chapters, we considered two methods for drawing the shear force distribution and bending moment distribution along the length of the beam. The first method was the method of sections, which in that method we considered some section cuts along the length of the beam, and based on the conventions that we have, the positive direction conventions, we considered the positive shear force and bending moment. Based on those conventions, applied that at the place of the section and analyzed the beam for finding that specific shear force and bending moment, which gave us an equation instead of some specific values. And by having all of those equations along the length of the beam, we could understand and obtain the shear force distribution and bending moment distribution along the length of the beam. After this, we also talked about a second method, which was based on the relationships between loading, shear force, and bending moment. This method was kind of easier to follow and it took less time, but the thing is that in cases where we have a complicated loading, it is not easy to use this second method. This method is basically based on looking at the configuration of the loading. Based on that, we can understand the shear force distribution based on the relationships between shear load and loading, and then based on the configuration of shear distribution along the length of the beam, we could understand the bending moment distribution in the beam. We talked about these methods, and now we are going to look at a few more examples to see how we can use these methods in understanding the shear force and bending moment distribution in beams. In the exam, if I want you to specifically use a certain method, I will specify it in the question. If I don't specify the method that you need to use for solving the problem, it's your choice for picking a method and understanding the shear force and bending moment distribution in a beam. So let's see which examples we have for today and how we can find the shear force and bending moment distribution based on those discussions. Over here you can see the first example, which is showing a beam with two supports, one hinge support over here and one roller support over there. And as you can see, we have a distributed load with a triangular shape, as you can see over here, and the dimensions are also given, and the amount of loading or the intensity of loading at the very end point is given as 27 kilonewton per meter. Then we have a distributed load with a triangular shape like this. We know that the intensity of the load is different in every location along the beam. For example, over here we have smaller intensity in comparison to this value, and as we get closer to the left end, the intensity of the load will be less, and we have to calculate the intensity of the load at each point along the beam to understand the loading and use it in our future calculations. I'm going to use the method of sections for this example, and then in the next example I will use the relationships between loading, shear force, and bending moment for drawing the shear force diagram and bending moment diagram. So this is the beam. Like the other examples that we had in structural analysis, the very first step is to draw the free body diagram and find the reaction. I have it over here. You can see the free body diagram is shown over here, and the reactions at this point, which is called point B, are here. We have a hinge support, 2 reactions, roller support over here, 1 reaction. I think by now you're completely familiar with this procedure and you know how to find these reactions. We have two reactions over here, one reaction over here. So summation of forces in x direction equal to 0 gives us the horizontal reaction at B as 0. Summation of forces in vertical direction equal to 0 gives us one equation for reaction at B and C. But since we have two unknowns, we have to write the third equation, which is summation of moments. Those are mentioned over here. But before this, let me also show you this step, which is understanding the situation of the beam. And it is not always necessary to have this. I usually repeat this in the examples that we have over here to just remind you about the procedure and show you how to use this in different problems. I think in one situation it was a bit confusing for some people to understand which equation to use, because we have this equation, we have another equation for truss structures, and we also have another equation for frames. In the case of exams or in problems that I give you for homeworks, I will specify which equation to use, because I know it may be a little confusing to, for example, if a frame is given, I have to use this equation, or I have to use the specific equation for frames. I will specify which equation to use, so don't worry about that. But in different examples that I have over here, I'm going to repeat this step in terms of finding the situation of the structure, to just know how to use it and kind of remind you about the procedure of understanding the condition and situation of the structure. We have three reactions, so R equal to 3 EC is the equations of condition. We said if we have a hinge inside the structure or roller inside the structure, they have their own specific EC values. Over here we don't have any of that, so EC equal to 0. Returning these values into this equation, we can see I is equal to 0, which means the structure is stable and determinate. Now we can move forward and write the equations for equilibrium. In x direction equal to 0, so Bx is found as 0. Summation of forces in vertical direction equal to 0. We have the equation for By and Cy, and then summation of moments about B over here equal to 0. We have the moment because of reaction at C, that should be positive Cy multiplied by 6, as you can see over here. And then the moment because of this triangular distributed load. The amount of load under this loading is equal to area under the load, which is 27 multiplied by 9 divided by 2. And then I have to find the centroid of this loading and find the distance from centroid to the point where I'm calculating the moments about. The centroid of this triangular shape is at 1/3 from the vertical side, or from this side, which is 3 meters right over here, 3 meters from the vertical side. And distance from centroid to the point where I'm calculating the moments about is 3 meters. And that is over here. I have a reminder for you at the end of this example. Over here, these are the very common shapes that we face and see in typical structural analysis problems, and even these two are the most common, and I have to say these two are not really used in regular problems, but in some cases you may see or you may face a parabolic shape of loading or more complicated situations. But these two, the rectangular form of loading and triangular form of loading, are the two common forms of loading in typical structures in civil engineering. So we could find the moments about point B, and based on that we could find the reaction at C, and then I can simply return this value into the second equation to find the reaction at B. And these values happen to be equal to each other. So this is the situation, and now I have to draw the sections, because in method of sections we need to have sections along the length of the beam and then derive the equations of shear force and bending moment for those sections. Over here I have the first section, and the other thing that you have to remember is the number of sections that you have to consider, and that depends on the loading that you have on the beam. Whenever you have a change in the loading along the length of the beam, you have to consider a specific section for that region. Point A is the beginning of the beam, so right after that I have to have a section. And then we have point B, which the reaction is applied, right? So right after that I have to have a section. And then from point B to point C, everything is the same, right? We have the same loading, there is nothing else applied to the beam, so I don't need any more sections in this region. So we have two sections, and I have to consider each section, consider the shear force and bending moment based on the convention, and then derive the equations for those regions. The first region is point A to point B, or x from 0 to 3. In this region, I have to consider the section AA, positive shear moment and axial based on the convention are mentioned over here. And then I have to write the equations of equilibrium for this region. Summation of forces in x equal to 0. There is nothing applied in x except the q, so q is equal to 0, which means beam does not have any axial load in this region. Then we can say summation of forces in y equal to 0. I have s downward, I consider positive as upward, and before writing the equation I have to mention that the positive convention that we talk about is based on the beam behavior, and this positive that I assume in the equations is just something that I assume. You can consider positive as downward and then write everything based on that. But this convention is not something that I can change. It is always based on what the kind of references are telling us to do. So this is not something that we can change or choose, but this positive that we have, this is just for the sake of writing the equation, and you can assume positive is downward and then change the way. For example, you say change the sign of the loading. If positive is downward, then you can say positive s plus the rest of the terms. This is your choice, but this is the convention, and that we have to always have that based on the behavior of the beam. This is just for the sake of writing the equation. This positive upward, or positive to the right, or positive counterclockwise. These are just for the sake of writing equations. So summation of forces in vertical direction equal to 0, and for that I can say s is downward, so minus s, and this loading is downward, so that should be negative. And I know for this situation in which we have a distributed load, the amount of load is area under the distributed load. Area under the triangle is the intensity of the load at the end multiplied by the length divided by 2. The intensity is a function of the location where we are looking at, or is a function of x, because we have a triangular shape. Based on the idea of similar triangles, I know if, for example, it is 27 at the end and 9 is the length, at some point over here where the length is x, the intensity can be found based on these ratios. The intensity divided by x is equal to this intensity at the end, or 27 divided by 9. And based on this, I can find the intensity at each point along the length as a function of x, which is 3x. So intensity is 3x multiplied by x divided by 2 is the area under the distributed load. And based on this, I can find s as minus 1.5x squared. This is the equation for shear force, of course, in this specific region. We could find the equation for shear force, and now let's find the equation for bending moment. Summation of moments about the section equal to 0. I'm assuming positive as counterclockwise, so positive m, and then I have the moments because of this distributed load. That is area under the load, again 3x multiplied by x divided by 2, and then the distance from centroid of the load to the place where I'm calculating the moment about. That is 1/3 of x, centroid of a triangle. So multiplied by x over 3 plus m, the moment that I have at the section equal to 0, and we can find the moment or the equation for bending moment as minus 0.5x cubed or x to the power 3. These are the equations for bending moment and shear force. And just for a quick check or something to check if our calculations are correct or not, based on the second method, we said shear force at each point is equal to the derivative of bending moment with respect to x. Later we will use this for solving another problems, but over here, just as a quick tool for checking our equations, we can check this by finding the derivative of bending moment with respect to x, and that should be equal to s, or shear. If it is not equal to the shear, then there is something wrong in our calculations and equations. So derivative of bending moment will be minus 1.5x squared, and as you can see, that is equal to the shear force equation that we found earlier, and that means that our equations are correct. So that was for the first section, and now let's move to the second section, BB, and see what is the situation over there. This is the section, this is the loading. Again, based on the conventions, I applied shear force, bending moment, and Q over axial load. Now this time X is in the domain of 3 to 9, 3 meter or point B to 9 or point C, the end of the beam. The intensity of the loading at the section based on similar triangles is 3x, and we have to write the equations of equilibrium. Summation of forces in x equal to 0, so Q is equal to 0. Summation of forces in vertical direction equal to 0, and based on that we can see or obtain the shear force equation. I'm not going to repeat the whole thing, it's very similar to the previous step. The only thing that is added to the situation is this reaction over here, so that is just a positive value since it is upward, and the same thing for bending moment. Because of this reaction, you can see the equation has more terms, but this is the situation for shear force and bending moment, and we could obtain the equations. Again, if you calculate the derivative of bending moment, it should be equal to the shear force equation. Now that we have the equations, the only thing that I have to do is to plot these equations in the regions. From x0 to x3, I have to plot this equation for shear force, and from x3 to x9, I have to plot this equation. And those are the equations. And the same thing for bending moment. The last step is to draw the qualitative deformed shape of the beam. And as we discussed during the presentation, whenever we have a positive moment, I have to plot a curve with positive concavity or concavity in the upward direction, like a ball in the upward direction, like this. And whenever I have a negative bending moment, I have to draw a curve with negative concavity or a ball which is downward, like this. And if you look at the beam, this is the kind of deformation that we expect from this beam. Like we have the loading, so it is going to go down, it is going to kind of go down under this loading. This support is going to keep just this point at its region, so there is going to be two curves, but the concavity of the curves should be based on the situation of bending moment, whether it is positive or negative. That was the first example, and I'm going to move to the second example and use the relationships between shear force and bending moment to solve this example over here. So let's draw the free body diagram of this example and see what is the situation about reactions. Over here you can see the free body diagram. We have hinge support over here, 2 reactions, roller support over there, 1 reaction, and based on these we can find the situation for the beam by considering this equation: 3 reactions, no internal hinge or roller, so E is equal to 0, and we can see I is equal to 0, which means the beam is stable and determinate. Then we can write the equations of equilibrium. Summation of forces in x equal to 0. As you can see, I have the reaction at this point, which I believe is point A. This is point A, and I think I mentioned the name of the points are mentioned here: A, B, C, and D. So we have a horizontal reaction at A, and there is also one other horizontal load or force, which is the horizontal component of this inclined load over here, right? So the horizontal component of this should be 50 multiplied by 3/5. That's what we have over here. So the horizontal reaction is found to be 30 kilonewton, and then I have to write the summation of forces in vertical direction equal to 0, and for that I have the vertical reaction at A and this reaction over there at the end of the beam, which is point D, and also we have the vertical distributed load, or this distributed load over here, and the vertical component of this force. Having all of them in the equation, we can obtain this equation over here for AY and DY. We have 2 unknowns, so I have to consider the third equation, which is summation of moments about 1 point. I'm considering the point as point A. The moments about point A are the moment because of this reaction over there, or at point D, the moment because of the vertical component of this force. This moment should be exactly or directly included in the equation, and the moments because of this distributed load. They are all mentioned over here. You can see over here the term because of distributed load, coupled or concentrated bending moment. This is the moment because of the vertical component of that inclined load or force, and the moment because of the reaction. Solving the equation, we can find the reaction at D as this term. I have to just fix this. The vertical reaction at D is found to be 78.78 kilonewton, and then returning that to equation 2, we can find the reaction at A as this value. So these are the reactions, and now I can use the relationships between loading, shear force, and bending moment to obtain the shear force diagram and bending moment diagram. Based on the rules, first we have to look at the loading, and then we have to consider or obtain the shear force diagram. We said whenever we have a point load, there should be a sharp change in the shear diagram, and the amount of change is equal to the point load. So shear at A is equal to the reaction as the value of the reaction. Then from point A to point B, we have distributed load. So the change in shear is equal to the area under the distributed load, that is 150. And because of that, we can say shear in B is equal to shear in A plus the change that we had between A and B. Since we have a distributed load, we know that the intensity or the slope of the shear distribution is equal to the intensity of the distributed load, right? That was the ds over dx equal to w. We had this term in the presentation files. But so based on that rule, we can say the slope of the shear diagram from point A to point B should be minus 10. The change is equal to minus 150, the change from A to B. And since we have a uniform distributed load, this is going to be a linear change and the slope is minus 10. That's what we have over here. See, from point A to point B, we have the change in shear from 111.2 to shear in B, which is minus 37.78. See, from point A to point B. And the slope is equal to minus 10. So that was from point A to point B. Now at point B, we have just a couple or a bending moment at this specific point, which has nothing to do with the shear force. So shear from point B to point C is going to be the same as whatever we had in point B. There is no loading. And then at point C, we have a point load. So there is going to be a sharp change in the shear, and that is equal to the magnitude of the point load, which is minus 40. So right before point C, shear was equal to minus 37.78. And right after C, we have to consider a drop in shear, and the amount of drop is minus 40. This is what is happening over here. So the shear was constant and then a drop equal to minus 40. The amount of shear at C is minus 37.78. That's what we had in this region. And because of this, right after C, the shear is minus 78.78. From point C to point D, again, there is no loading, no point load or distributed load. So shear is the same from point C to point D. At point D, I have a concentrated load or a point load, and that's why the shear should see a sharp change, and the amount of change is equal to 78.78. That's what we have over here. Minus 78.78 was the shear before reaching point D. At point D, we have the reaction, and then applying that, the shear at the end of the beam is equal to 0. So applying the rules based on the relationship between shear force and bending moment, we could find the shear diagram like this. And now we can look at the shear diagram and find the bending moment diagram. We know the area under the shear diagram is going to be the change in the bending moment diagram between the points, and the slope at each point in the bending moment diagram is equal to the shear at each point, right? Whenever I see, for example, a linear change in the shear, that means that the derivative of bending moment is a line, which means the bending moment is a parabolic shape. So let's apply the rules. At point A, I have no bending moment, because we said if you have a bending moment at a point, the change in the moment diagram is equal to the magnitude of that bending moment or couple. So there is nothing over here as a reaction. So at point A, bending moment equal to 0. From point A to point E, we have positive shear, and it means that the area under this diagram is going to be the change in the bending moment, and since it is changing linearly, the bending moment is going to change in a parabolic shape. The change from point A to point E is equal to area under the shear diagram. I found this area, and that is 618.38 kilonewton meter. And then at point E, which is some point over here, we have no bending moment, it's just loading. I'm trying to find or see if there is any bending moment at a specific point or couple. Since there is nothing from point A to point B, we can just consider this as the change in the bending moment. And that's what we have over here. As you can see, from point A to point E, see point A to point E, this is the change in the shear. And now you can see at point E, the shear is equal to 0, right? That means that the slope of the bending moment should be equal to 0, because the slope of the bending moment diagram is equal to shear at each point. Shear over here is equal to 0, so the slope in bending moment should be equal to 0 at that specific point. Then we have this diagram from point E to point B. As you can see, the shear is negative, so the amount of bending moment should be reduced, and the amount of change should be or is equal to area under the shear diagram. From point E to point B, I can find the area under this triangle as minus 75.23 kilonewton meter. So I have to add this to the amount of bending moment that we had at point E, which was 618. Adding these, you can see at point B, my bending moment is 543. That is what we have over here. Exactly at point B, we have this couple over here. So it means that there is going to be a sharp change in the bending moment because of this bending moment at this specific point or this couple. Is it going to increase or decrease my bending moment? Or in other terms, is it going to be positive or negative? One way to understand that is to just consider a very sharp section right after that couple like this over here. And based on the conventions, you can see M minus 162 equal to 0, and that's why M is positive 162 right after that couple. I'm looking at right after this couple over here to understand it is going to increase the bending moment or decrease the bending moment. Since this is a positive moment, it is going to increase, and the amount of increase in the bending moment at point B is equal to the magnitude of that couple over there, which was 160. So before point B, based on those calculations that we had, the bending moment was 543, and right after B, we have this increase as 162, and the bending moment is 705.15. So right now we are right after point B. And if I look at the shear diagram, which is the important diagram to look at for obtaining the bending moment, we are right after B. So from point B to point C, the shear is a constant value, right? The intensity of shear is minus 38.78. When the shear is a constant value, it means that the slope of the bending moment is a constant value, which means it is going to have a linear shape. The slope is minus 38.78, and the change in a linear way is going to be area under the shear diagram. Area is from point B to point C is found over here. Area under the shear diagram, or change in the bending moment diagram, is found to be minus 232. So from this point we found the moment as 705. We have to go down or reduce the moment in a linear way to point C, and the amount of change is minus 232 as we found over here. So we could find the moment at C as 472.47 kilonewton meter. And now from point C to point D, again looking at the bending moment at the shear force diagram, the shear force is changing. It is not changing, it's just a constant value, which means that the slope of the bending moment is equal to the amount of shear. The shear is minus 78.7, so the slope of the bending moment diagram should be minus 78.78, and the change is under the shear, the area under the shear diagram. We found this area over here, that is minus 472.68. Adding this to the value that we had over there, you can see it is approximately 0. The amount might be a little off from 0, and that's because of the rounding errors that we have in our calculations. But it makes sense, because if you look at the beam, There is no bending moment at the end, and it is a roller support, which means that there is no bending moment at this end point of the beam. And based on these calculations, you can see at the end we could find MD as 0. And this is the change in a linear way from point C to point D. So by applying the rules, we could find the shear force and bending moment diagram of this beam. And the last step is to draw the qualitative deformed shape. And again, let's take a look at the beam. You can see this is the beam. I have some loading, right? This is the loading, this is the vertical loading, so it is going to move down. And I said the only thing that we need to take care of is the concavity. It should be upward or downward. And since we have a positive bending moment along the whole length of the beam, it should be a positive concavity or upward concavity like a ball during the whole length of the beam. And this is the situation for the qualitative deflected shape of the beam. So this was the second example, and one thing that I need to say about this is to have these rules in mind whenever we are using these relationships between loading and shear force and bending moment to obtain the results. Whenever we have a point load, that point load will be a sharp change in the shear force, and the sharp change in the shear force means that there is going to be a change in the slope of the bending moment diagram. Whenever we have a uniformly distributed load like this, it means that we are going to have a linear change in the shear and parabolic change in the bending moment. Whenever we have a point, a couple or a bending moment at a specific point, it is going to do nothing for shear diagram, but because of this, there is going to be a sharp change in the bending moment diagram. If you have these rules in mind, then you can simply follow these steps that I have over here and obtain the shear force and bending moment diagram. So these were the rules for this part, and now let's take a look at the third example, which is this one over here, and see how we can find the shear force and bending moment diagram for this example based on the method of sections. So here is the third example, and I'm going to use the method of sections for obtaining the shear force and bending moment diagrams. I'm not going to repeat the whole thing again because I already explained it in the first example. I'm going to just show you the general procedure and point out the major differences that we have in this example over here. As you can see, we have a hinge over here, and it means that we have to take advantage of it in terms of and in the procedure of analysis. We have three reactions over here. We have a fixed support over there at the left end. We have a roller support over here at this point, which means one reaction over here. And if I draw the free body diagram, this is the situation. As you can see, we have 1, 2, 3, 4, 5 reactions. And if I just consider these alone, I may not be able to find these reactions by just drawing using the equations of equilibrium. We have 3 equations. Over here we have 4 unknowns, which means that those equations will not be enough. But the thing that helps us is this hinge over here. You can see the static determinacy. The only thing that we have to consider is EC equal to 1 because of this hinge. And then you can see because of that, the total or the final value for I is equal to 0, which means the structure is stable and determinate. Excuse me. Finding the reactions, we have summation of forces in x equal to 0, summation of forces in vertical direction, and summation of moments about A. As you can see, the number of unknowns are greater than the number of equations. That's why I'm going to break it from point B, and then we will have this situation over here. The thing that you have to have in mind is to consider this situation. Let's say I'm looking at section AD or segment AD. I don't know the direction of forces at B, so just assume something, but make sure on the other side you are putting the reactions of these over there. That's the important thing. The reaction of forces on one side of the hinge should be applied on the other side of the hinge. So when you put these together, there will be nothing left and they can balance each other and cancel each other out. So this is the situation, and now I'm going to write the equations of equilibrium for this segment. As you can see in this specific segment or segment BD, we have 3 reactions. We can write 3 equations and simply we can find all the unknown values. Bx is found as 0, By and Cy can be found by writing the equations in vertical direction and moments about point B. I found them over here, and then I return the reaction at I return the reactions that I found over here as C into the general equation that I had over here to find the reaction at A. And then also you can see the rest of the steps are found by just returning the values that I find into the equations that I have over here for finding the other unknown values. You can use this segment AB to find the reactions at A, or you can return the values or reactions that you find over here into these equations that you had already and find the unknown values. That's your choice. I decided to use the equations that I had already and return the values that I find from segment BD into these equations to solve the reactions and find them. After finding the reactions, you have this situation, and now we are going to consider some segments along the length of the beam or sections along the length of the beam and write the equations of equilibrium for each of those sections. We said the number of sections is a function of the loading that we have along the beam. As you can see, from A to B, I only have the reactions at A and then nothing from A to B. So because of this situation over here, there should be one segment right after beginning of the beam. Then nothing happens from A to B, so this section is enough. From B to C, I have the hinge and also beginning of the distributed load. So I have to consider a section from B to C. And then at C, I have a point load, which is the reaction. So another section after point C. That is the sections that we need to consider. So 3 sections. And now based on the conventions, I'm going to assume the section, the shear, moment, and axial after the section, and then write the equations of equilibrium for each region. We did this in the first example. I'm not going to repeat the whole thing. Just follow these procedures that I have when you are solving this at home. And if you have any question, let me know. We can discuss this. But everything is very similar to what we did in the first example. I'm just trying to find if there is any big difference that I need to explain. But everything is very similar to what we did in the first example. The distributed load is a uniform distributed load, which is easier than that triangular shape. So it shouldn't be a problem to find the moments about the section that you have in your problem. And that's the thing. And then we have the third section over here after point C. And we could find the equations as you can see over here. Having all the equations, I have to just plot each equation in each domain that we have for the problem. From x0 to 10, I have to plot this value. Shear force is just a constant value, so it is not the equation. For this domain, from x10 to 20, I have this equation, so I have to plot this. And then 20 to 25, I have to plot this equation, which again, as you can see, this is not even an equation, it is just a constant value. So this is the shear diagram based on the equations that we have. And by applying the same idea, I can plot the equations for the bending moment diagram, and you have to obtain this. After this, we have the qualitative deflected shape. Again, you have to look at the situation of the beam. This is the beam. We have loading from point B to point C, so it is going to push the beam down. and then we also have a loading over here, so it is also going to push the beam down. So we are going to have some curves below the level of the beam as the deflected shape. Make sure you don't, or you return the curve up to its original shape at point C, because we have a roller support. It is not going to move down at this point. And the only thing is to consider the concavity of that curve. Wherever we have a positive bending, concavity should be upward, and wherever we have negative, which is majority of the beam, concavity should be downward. That's what we have over here. Negative bending curve with concavity downward, then positive bending in this small amount, so curve with positive concavity, and then from point F to the rest we have negative concavity, and based on the boundary conditions or supports that we have, this should return to the original point and then move down. You can look at the loading and get some guess and idea about the deflected shape. The only point that is the detail that you have to consider in your qualitative deflected shape is the sign of bending moment and the concavity of your curves. So let's move to the fourth example and see what is the situation for this beam over here. This one is carrying a uniformly distributed load. We have 3 supports and also 1 hinge over there. I'm gonna use the relationships between loading, shear force, and bending moment to obtain the results of this problem over here. So the steps are the same. We have to draw the reactions: roller support, hinge support. As you can see, the number of reactions are greater than the number of equations of equilibrium, so we have to take advantage of this hinge in breaking the beam and then write the equations for those separated segments, and through that approach we can find the reactions. Over here I used these equations and terms to understand the situation. Pay attention to this EC, which is the equations of condition because of this hinge. Then I try to find the reactions by writing the equations of equilibrium for the total beam. And as you can see, the number of unknowns are greater than the number of equations. That's why I considered separated segments of the beam, and the separation is happening from the hinge. Pay attention to the way that I am putting the forces at point C. I don't know the forces, so I just assume them as this at one segment and then put the reactions of them on the other segment. Right? Following this procedure, now we can write the equations of equilibrium for each of these segments. It doesn't matter whether you consider this one or this one. Just considering one of these segments will help us to find the reactions on that specific segment, and then once we find that, we can return those values to the equations that we had already for the total beam and find the reactions for the beam. Or you can solve these 2 segments separately, and by solving them separately you can find the reactions without the need to go back and use the equations that you had for the total beam. It's your call, and you can pick any of these 2 approaches. So I have the segment CD over here. I'm writing the equations of equilibrium for just this segment, and by doing that I could find the reactions at D and the forces at hinge C. So after this I move to segment AC, write the equations, and I could find the reactions at A and B. After this we have this situation, and now I'm going to apply the rules to find the shear force and bending moment diagram. Whenever we have a point load, there is going to be a sharp change in the shear force diagram. Whenever we have a distributed load, uniformly distributed load like this, the shear diagram is going to change in a linear way, and the slope is equal to the intensity of the distributed load. Over here it is 2, so the slope should be -2 because it is downward. The change in the shear diagram is area under the loading, that's what I calculated in each of these lines over here. If you just follow these lines, you can see how could I find the shear at each of these points, and then the changes in shear diagram are equal to the area under the loading that we have in our beam over here. So based on these, I could find the shear diagram, and then area under the shear diagram is equal to the change in the bending moment diagram. If we have a couple or bending moment at a specific point, that will be a change, a sharp change in the bending moment. We don't have such a thing over here, so there is going or we are not going to have any sharp change in the bending moment diagram. It is going to be continuous. Then whenever we have a linear change in the shear, the bending moment is going to be a parabolic shape, because the derivative of bending moment is shear. And those are the things that you have to have in mind. If, for example, instead of having a linear shape, I have a constant shape for shear, that means that the bending moment is going to change in a linear way. So in each of these lines, I calculated the bending moment after each of these points. You can just follow the situation and see what is the change, and based on these, I could find the bending moment diagram like this over here. It is parabolic because shear is linear, and each of these values are found based on area under the shear diagram. I think if you just follow these lines, you can clearly see how I calculated this. And having this bending moment diagram, you can simply find the qualitative deflected shape based on the loading that you have. See, this is the loading. I know the beam is going to move down because of this loading. The thing is that the concavity should be upward or downward, and that can be determined based on the positive or negative bending. As long as you have positive bending, it should look like a bowl. And whenever you have a negative bending, you have to consider an upside down bowl like this. So this is the qualitative deflected shape. It should be pretty straightforward. If you have any question, don't hesitate to send me your question and we can discuss it more. I didn't repeat all the details because it is going to be very similar to what we had in the second example. But if you think we need to discuss it more, don't hesitate to send me an email and we can discuss it in more details. That was the fourth example, and over here the last example is a frame, which we are going to find the shear force and bending moment distribution in the frame. Again, this frame, as I talked about it in the presentation file, is basically a combination of beams in different orientations. And I have to say it's going to take lots of time, so it is impossible to have a frame analysis in the exam. But I'm gonna give you one problem to solve in your homework. But in the exam, there's going to be no question about frames because it's gonna take lots of time to just analyze one frame and do all the shear force and bending moment diagrams for a frame. So the methods are very similar to what we had in the presentation file. First, drawing the free body diagram like this. Then I have the equation for understanding the condition. M number of members, R number of reactions, J number of joints. So as you can see, I have two members, so M is equal to 2. R is the reactions. I have a fixed support, and we have 3 reactions at a fixed support like this. 1 horizontal, 1 vertical, and 1 bending moment. J is the number of joints, 1, 2, 3. Or let me show you the structure. So this is the frame. I'm considering each of these points as a joint. So we have 3 joints, EC equal to 0, and that's why if I put these values into this equation, we have the final value as 0. Again, the way that we have or we can find the values of M, R, or J. R is the number of reactions. We have to always have that as the reactions, but counting the number of members and joints depends on the way you are looking at the structure. You can see maybe some people say this is just one big member without any joint, and then change those parameters in the equations based on that and get the same result. That depends on the assumptions that you have, but these are different ways that you can solve this situation for the frames. After finding the situation, we can write the equations of equilibrium. Since we had only 3 unknowns, I could simply find the reactions by considering the equations of equilibrium. And then the important point for analyzing the frames is breaking the members in the frame into different parts, as we did in the presentation file and in the last example that we had in the presentation file. So as you can see, I'm considering member A, B, and B, C and separate them from the frame. And then after that, I'm gonna just consider some forces in the members and then reaction of forces in the joints. You can look at the presentation file to see more details about it, but consider different parts as A, B, and B, C. Just assume some forces in the place of the joints. We have rigid joints over here, which means that bending moment can be moved and transferred through the members. And then analyze each of these members, or we can say beams. And once you analyze them, make sure you put the reaction of the forces that you have at the end of the beams at the place of the joints and then transfer them to the other member. You can look at the presentation file and the example that I solved at the end of the presentation file, and those procedures or that procedure is exactly followed over here, and we have these steps in terms of the calculation. We have member AB. These are the reactions that are coming from support A over here. So based on those, I could find the forces at the end B, and then I just consider the reaction of these forces at joint B, as you can see over here. These are just at first I didn't know these forces, so I just assumed something at end B and then applied the reaction of these on the other side of B at joint B. And the same idea is happening on the other side. These are coming from member BC. Since it was pretty straightforward, I didn't show it, but I had member BC. I guessed some loading over there and applied the reactions over here. Over here on the other side of joint B. Joint B is just a joint with 0 length, so it means that the bending moment should be exactly the same. That's what we have over here on 2 sides of the joint, and summation of forces and summation of forces in X and Y direction. You can just look at the equations, it should be pretty clear to follow. And then as you can see, I have the member BC over here. I had some reactions at joint B, which at first I didn't know, so I assumed something, and then exactly the reaction of those at point B. So the steps are considering different segments, considering different members like BC and AB, assume something at the ends of the members, and put the reaction of those at the location of the joints that you have in the frame. That's the procedure we followed in the presentation, and what we had over here is just the same procedure. Once you follow this procedure, at the end you will have these beams. Instead of a frame, you have these separated beams with the loading and reactions acting as a loading on the beams. And now you have to analyze these beams very similar to what we had in earlier examples. And once you analyze them, you can simply obtain the shear force and bending moment diagrams. Once you have the bending moment diagrams, you can draw the qualitative deflected shape based on the same ideas that we had for beams, and that is also possible by just looking at the situation. So I'm pushing the frame from the side, so it is going to move to the right. I'm also pressing it down with this distributed load, so it is going to move right and a bit down. And that is what we have as the qualitative deflected shape of the beam. Let me know if there is a question over here. I thought it is pretty clear and straightforward to follow. That's why I didn't go into the details and explain them again. But if you have any question or if you think we need to discuss it more, don't hesitate to send me an email and we can definitely discuss it through WebEx or even the emails.